Alright, chapter 2 is mechanics. The first portion of mechanics is kinematics. Kinematics is the section that deals with displacement, velocity, distance, speed, etc. All kinds of calculations that don't involve the mass of the object involved. So, firstly, you need to define distance, displacement, speed, velocity, and explain explicitly the difference between a scalar quantity and a vector quantity. So, your scalar quantities would be distance and vector, the corresponding vector quantity will be displacement. You can choose one example to actually define all of these. For example, a person walking across a room which is 2 meters in length and then walking back. So give a one-dimensional example first to let the student understand, and then you can elaborate that this holds true in 2 dimensions and 3 dimensions as well. So then you can also move on to explaining that the rate of change of distance is speed and the rate of change of displacement is velocity. And then explicitly mention that acceleration is the rate of change of velocity and not speed. So once you've defined these and the student understands this, you can probably in the same example chart out all these values in graphs. Make sure you show the distance versus time graph, speed versus time graph, displacement versus time graph, velocity versus time, and acceleration versus time. Okay, then what I do is I use graphs in order to derive the equations of motion under constant acceleration. So firstly you need to explain, for example in part 2.1.3 the conditions under which you can use the 3 equations of motion, and the condition is simple, that the acceleration must be constant. So you want to let them know what are the conditions under which these equations will not hold true as well. 2.1.2 is basically defining the difference between instantaneous and average values of speed, velocity, etc. Instantaneous values are at that very instant, so you take the gradient. Instantaneous, you will take the gradient at that point in the graph. Okay. For example, if you want to find the instantaneous velocity, you will take the gradient of the distance time graph, the displacement time graph at that particular instant. But if you had to find the average value of velocity, so you have to see the displacement time graph, cover the total displacement, and then divide it by the time taken. So you want to mention those things as well. So make sure you elaborate that the average value will be the total displacement or the total value divided by the time taken. Okay, so then you would want to derive the 3 equations of motion using graphs, and make sure the best examples for this would be in 2.1.4. Where you're using a body falling in vacuum near the Earth's surface. That's a condition where the acceleration is constant. 2.1.6, you want to define you want to describe the effects of air resistance on falling objects. So you can mention how, as the body is falling, and its velocity goes on increasing, the value of air resistance goes on increasing as well. A good example for this is a parachutist or a skydiver jumping off from an airplane, how the air resistance increases, and you can show how the velocity changes over time. So that's a good example to describe this section. Then, like I said, you want to draw the graphs for all these values and show the relationship between them. For example, you want to show them that if you have a displacement versus time graph and you take the gradient, you will get the velocity, right? And if you have a velocity versus time graph and you take the gradient, you will get the acceleration. And in an acceleration versus time graph, if you take the area under the curve, you should get the value of velocity. Area under, and also if you take the area under the velocity versus time graph, you should get the displacement. Okay, then just give the student a few examples on how they can work out the graphs and get this information from the relevant graphs. Yeah, that's it. The end portion 2.1.9 is determining relative velocity in 1 and 2 dimensions. This is basically kind of a repetition of the portion on vectors. So this is just vector addition and subtraction, which you would probably need to go through. So yeah, that covers kinematics. Okay, so second part of mechanics is dynamics. So dynamics is the portion which is related to forces and all kinds of equations and all kinds of calculations related to which would include the mass or the characteristics of the object that we're talking about. So make sure that you make this distinction between dynamics and kinematics so that the students can identify in the exams. Okay, how you want to follow this, the flow of the portion, the chapter over here, is up to you. What I like to do is I first go into defining the three Newton's laws of motion, okay, and one by one I explain how they're relevant. So firstly, after you explain what's Newton's first law, the law of inertia, that an object will continue to stay in a state of rest or continuous motion unless acted upon by an external force, okay. Then you mention a few examples of this, and when you're explaining the law of inertia, you can also talk about translational equilibrium, that when a body is does not have any external force acting on it, net external force, which means there could be external forces, but they probably balance each other out, and therefore the net external force is zero, and therefore the body is in translational equilibrium, and it continues to either move at a constant velocity or stay in its state of rest. So you want to mention that, and when you do that, after that you can move on to Newton's second law. F equals ma is basically what it states, but the definition would be the force acting upon, the net external force acting upon a body is directly proportional to its rate of change of momentum. So you want to make sure you elaborate on that. Momentum, you should define what momentum is. Momentum is mass times velocity, and so the rate of change of momentum would be force. From here you can tell them that the change in momentum, okay, another way of writing this would probably be the change in momentum over the change in time. So the rate of change of momentum. It identified that the change in momentum is actually called impulse. Final momentum minus initial momentum is impulse. So therefore, if you have a force which varies over time, right? Force in newtons, time in second. If you have a force that is varying with time, you can find the impulse by taking the area under the graph. Okay, one useful tip to let them know what can you find by taking the area under the graph. Just ask them to divide force, rather multiply force with time and see what kind of a value do they expect to get. Force multiplied by time is going to give you change in momentum or impulse. So that would tell you what is the quantity that you would get, or what value would you get if you take the area under the graph. Also, when you're talking about this, you could also probably say, if you had to take the gradient of a certain graph, what quantity would you get? Just divide the y value with the x value and you should be able to see what kind of a value would you expect. So in this case, it's the rate of change of force. So yeah, that's the value that you would get by taking the gradient at a certain point. Okay, so force multiplied by time That's the area under the graph, and that should give you the impulse. Now, impulse or the change in momentum. So once you've done that, you can also talk about Newton's third law. Newton's third law states that every action has an equal and opposite reaction. Now, you want to mention the other form of Newton's third law, which mentions that if body A exerts a force on body B, then body B would exert an equal and opposite force on body A. So you can take elaborate this using an example. Say for example, this is the planet and there's a man standing on the planet. So you want to draw the forces here. For example, the weight acting down on the man, right? So that's the force exerted on the man by the earth, right? So you want to make sure that they understand that there is a normal reaction on the man, force on the man by the ground. Okay, these two are not an action-reaction pair. Why? Because this force is being acted upon the man from the earth, a gravitational force. Therefore, the reaction pair for this would be the force of attraction on the earth by the man. Alright? So, as the earth is pulling the man down, the man is also pulling the earth towards himself with the same force. The only difference is that the earth is so massive that the acceleration produced in it is very slow, very little. Therefore, the man would fall to the earth rather than the earth falling towards the man. So you want to elaborate this, that the action-reaction pair must be on the same two objects that we're talking about, body A and body B. For this force, for example, the force acting upon the man due to the ground, there's a reaction pair which is the force acting on the ground due to the man. So that's another action-reaction pair. They are equal and in opposite directions. So this is an action-reaction pair for this, and this here is also an action-reaction pair. Okay? So you can probably use such an example to let the student identify action-reaction pairs. Okay. Once you've done that, you can probably go into letting the students know how they should go about solving problems.